Good day everyone, this is Angel Tambak and my topic is all about Chapter 8, Solvable and Nilpotent Groups. Definition 8.1.1. Let G be a group and G is equal to H sub 0 is a superset of H sub 1 is a superset of H sub 2 is a superset ... is a superset H sub n is equal to identity be a chain of subgroups of G. The chain is called a subnormal series of chain if each H sub I is normal in H sub I minus 1. The chain is called a normal series of chain if each H sub I is a normal in G. The chain is called a composition series if each H sub I is a maximal normal subgroup of H sub I minus 1. That is, H sub I is not equal to H sub I minus 1, and if H sub I is a proper subset of H is a subset of H sub I minus 1 and H is normal in H sub I minus 1, then H is equal to H sub I minus 1, I is equal to 1 to ... n. The number of proper inclusions in the chain is called the length of the chain. The groups H sub I minus 1 divides H sub I are called the factors of the chain. In definition 8.1.1, if H sub I minus 1 is equal to H sub I, then the group H sub I minus 1 divides H sub I consists of a single element and is called a trivial factor of the chain. Hence, the length of the chain is the number of non-trivial factors H sub I minus 1 divides H sub I of the chain. Every group G has a normal chain, namely, G is a superset of identity since identity is a normal subgroup of G. Furthermore, it can be shown by induction on cardinality of G that every finite group G has a composition series. We see in a composition series G is equal to H sub 0 is a superset of H sub 1 is a superset of H sub 2 is a superset ... is a superset H sub n is equal to identity for a group G that the factors H sub I minus 1 divides H sub I are simple groups. In some sense, the examination of G has been reduced to its composition factors. Example 8.1.2. Consider the symmetric groups S sub 4 set H sub 1 is equal to a set of identity 1, 2, 3, 4, 2, 1, 4, 3 of 1, 2, 3, 4, 3, 4, 1, 2 of 1, 2, 3, 4, 4, 3, 2, 1 and H sub 2 is equal to a set of identity 1, 2, 3, 4, 2, 1, 4, 3. Now, S sub 4 is equal to H sub 0 is a proper superset of H sub 1 is a proper superset of H sub 2 is a proper superset of H sub 3 is equal to identity is a subnormal chain which is not a normal chain since H sub 2 is not normal in S sub 4 even though H sub 2 is normal in H sub 1. Definition 8.1.4. Let G be a group and G is equal to H sub 0 is a superset of H sub 1 is a superset of H sub 2 is a superset ... is a superset of H sub n minus 1 is a superset of H sub n is equal to identity be a subnormal series in G. A one-step refinement of this series is any series of the form G is equal to H sub 0 is a superset of H sub 1 is a superset is a superset of H sub I minus 1 is a superset of H, a superset H sub I is a superset is a superset H sub n minus 1 is a superset H sub n is equal to identity, where H is a normal subgroup of H sub I minus 1 and H sub I is a normal subgroup of H. I is equal to 1 to n. A refinement of 8.1 is a subnormal series which is obtained from H.1 by a finite sequence of one-step refinements. A refinement G is equal to K sub 0 superset K sub 1 superset K sub 2 superset superset K sub m minus 1 superset K sub m is equal to identity of 8.1 is called a proper refinement if there exists a subgroup K sub J in 8.2 which is different from each H sub I of 8.1. Thus, a chain of subgroups G is equal to K sub 0 is superset K sub 1 is superset K sub 2 is superset is superset K sub m minus 1 superset K sub m is equal to identity of G is called a refinement of a chain of subgroups G is equal to H sub 0 is superset H sub 1 is superset H sub 2 is superset is superset H sub n minus 1 superset H sub n is equal to identity of G if H subs or a set of H sub 0, H sub 1, H sub 2 H sub n is a subset of a set K sub 0, K sub 1, K sub 2 K sub m and is called a proper refinement if a set of H sub 0, H sub 1, H sub 2 H sub n is a proper subset of a set K sub 0, K sub 1, K sub 2 and K sub m. Example 8.1.5. Consider the normal series Z is a proper superset of 6Z is a proper superset of 12Z, a proper superset of 48Z is a proper superset of a set 0. The subnormal series Z is a proper superset 2Z is a proper superset 6Z, a proper superset 12Z is a proper superset 48Z is a proper superset of a set 0 is a one-step refinement of 8.3. Again, the subnormal series Z is a proper superset of 2Z is a proper superset of 6Z is a proper superset of 12Z is a proper superset of 24Z is a proper superset of 48Z is a proper superset of a set 0 is a one-step refinement of 8.4. From the definition, it follows that both 8.4 and 8.5 are proper refinements of 8.3. In example 8.1.3, Z sub 12 is a subset of the set generated by the element 6, which is also a subset of the set generated by the element 0 is a refinement of Z sub 12 is a subset of the set generated by the element of 6, which is also a subset of the set generated by the element 0, while Z sub 12 is a subset of the set generated by the element of 2, which is a subset of the set generated by the element 4, which is also a subset of the set generated by the element 0 is not. Theorem 8.1.7. A subnormal series in a group G is a composition series if and only if it has no proper refinement. Proof. Let G is equal to H sub 0 superset H sub 1 is superset H sub 2 is superset ... is superset H sub n minus 1 is superset H sub n is equal to identity be a composition series. Let G is equal to H sub 0 is superset H sub 1 is superset ... is superset H sub I minus 1 superset H is superset H sub I is superset ... is superset H sub n minus 1 is superset H sub n is equal to identity be a one-step refinement of 8.6. Since 8.6 is a composition series, H sub I is a maximal normal subgroup of H sub I minus 1. Thus, either H is equal to H sub I minus 1 or H is equal to H sub I. Hence, it follows that 8.6 has no proper refinement. Conversely, suppose that G is equal to H sub 0 is superset H sub 1 superset H sub 2 superset ... is superset H sub n minus 1 is superset H sub n is equal to identity is a subnormal series which has no proper refinement. Suppose 8.8 is not a composition series. Then, there exists a subgroup H sub I in 8.8 such that H sub I is not a maximal normal subgroup in H sub I minus 1. Thus, there exists a subgroup H such that H sub I minus 1 is not equal to H sub I. H is a normal subgroup of H sub I minus 1 and H sub I is a normal subgroup of H. This produces a proper refinement of 8.8, a contradiction. Hence, 8.8 is a composition series. Definition 8.1.8. Two subnormal chains for a group G. G is equal to H sub 0 is superset H sub 1 superset H sub 2 is superset ... is superset H sub n minus 1 is superset H sub n is equal to identity and G is equal to K sub 0 is a superset K sub 1 is a superset K sub 2 is superset ... is superset K sub m minus 1 is superset K sub n. M is equal to identity in 8.10 are called equivalent if there is a 1-to-1 correspondence between the non-trivial factors of 8.9 and 8.10 such that corresponding factors are isomorphic. If the normal chains 8.1 and 8.10 are equivalent, then the length of 8.9 equals the length of 8.10. Example 8.1.9. Consider the subnormal series Z is a subset of 4Z is a subset of 12Z is a subset of 24Z subset 12 Z or 120Z is a subset of a set 0. Z is a subset, 2Z is a subset, 8Z is a subset, 24Z is a subset, 120Z is a subset of a set 0. The factors of 8.11 are Z divides 4Z is equal to 4Z4 or Z sub 4. 4Z divides 12Z is equal to Z sub 3. 12Z divides 24Z is equal to Z sub 2. 24Z divides 120Z is equal to Z sub 5, and 120Z divides the set of 0 is equal to Z. And the factors of 8.12 are Z divides 2Z is equal to Z2 or Z sub 2. 2Z divides 8Z is equal to Z sub 4. 8Z divides 24Z is equal to Z sub 3. 24Z divides 120Z is equal to Z sub 5. And 120Z divides a set of 0 is equal to Z. Hence, there exists a 1-to-1 correspondence between the factors of 8.11 and 8.12. Consequently, 8.11 and 8.12 are equivalent. Theorem 8.1.10. Zassenhaus lemma. Let H prime, H, K prime, and K be subgroups of a group G such that H prime is a normal subgroup of H and K prime is a normal subgroup of K. Then H prime of H intersection K prime is a normal subgroup of H prime of H intersection K, and K prime of H intersection of H prime intersection K is a normal subgroup of K prime of H intersection K. Furthermore, H prime of H intersection K all over H prime of H intersection K prime is equal to K prime of H intersection K all over K prime of H prime intersection K. Proof. From the hypothesis, it follows that H intersection K prime and H prime intersection K are normal subgroups of H intersection K. Thus, H intersection K prime of H prime intersection K is a normal subgroup of H intersection K. Set J is equal to H intersection K prime of H intersection K. Define the function f H prime of H intersection K to H intersection K divides J as follows. If A is an element of H prime of H intersection K, then A is equal to H prime B, where H prime is an element of H prime is equal to B is an element of H intersection K. Set F times A is equal to GB. Let A sub 1, A sub 2 is an element of H prime of H intersection K. Then A sub 1 is equal to H prime sub 1, B sub 1. A sub 2 is equal to H prime sub 2, B sub 2 for some H prime sub 1. H prime sub 2 is an element of H prime and B sub 1. B sub 2 is an element of H intersection K. Suppose A sub 1 is equal to A sub 2, then H prime sub 1, B sub 1 is equal to H prime sub 2, B sub 2. Thus, H sub 2 or inverse H sub 2, H prime sub 1 is equal to inverse B sub 2, B sub 1 is an element of H prime intersection of H intersection K is a subset of H prime intersection K is a subset of J. Hence, JB sub 1 is equal to JB sub 2, and so F of A sub 1 is equal to F of A sub 2. Thus, F is well defined. Since H prime is a normal subgroup of H, B sub 1, H prime sub 2, and or inverse of B sub 1, H prime sub 2, B is an element of H sub 1. Now, A sub 1, A sub 2 is equal to H prime sub 1, B sub 1, H prime sub 2. B sub 2 is equal to H prime sub 1, B sub 1, H prime sub 2, B sub 1, inverse. B sub 2, B sub 1, B sub 2 is equal to H prime, B sub 1, B sub 2, where H prime is equal to H prime sub 1, B sub 1, H prime sub 2, B sub 1, inverse is an element of H prime. Hence, F of A sub 1, A sub 2 is equal to GB sub 1, B sub 2 is equal to GB1, or GB sub 1, GB sub 2 is equal to F of A sub 1, F A sub 2. Therefore, F is a homomorphism. From the definition of F, it follows that F maps H prime of H intersection K onto H intersection K divides J. Also, it is easy to verify that ker F is equal to H prime of H intersection K prime. Hence, by theorem 5.2.2, H prime of H intersection K all over H prime of H intersection K prime is equal to H intersection K over J. By symmetry, K prime of H intersection K all over K prime of H prime intersection K is equal to H intersection K over J. Finally, the desired isomorphism follows from these two isomorphisms. Theorem 8.1.11 square. Any two subnormal series G is equal to H sub 0 is a superset H sub 1, superset H sub 2 is a superset ... is a superset H sub n minus 1 is a superset H sub n is equal to identity G is equal to K sub 0 is a superset of K sub 1 is a superset K sub 2 is a superset ... is a superset K sub m minus 1 is a superset K sub m is equal to identity of a group G have refinements which are equivalent. Proof. Between each H sub I and H sub I plus 1, insert the group H sub I plus 1 of H sub I intersection K sub I. J is equal to 0, 1, 2, ... m. From the normality assertion of the Zassenhaus lemma, this refinement of 8.13 is a subnormal chain with Mn not necessarily strict inclusions. Between each K sub j and K sub j plus 1, insert the group K sub j plus 1 of K sub j intersection H sub I is equal to 0. 0, 1, 2, ... n. The refinement of 8.14 is also a subnormal chain with Mn inclusions. The final refinements are ... superset H sub I plus 1 of H sub I is intersection K sub I is superset H sub I plus 1 of H sub I intersection K sub j plus 1 is a superset ... and ... is a superset K sub j plus 1 of K sub j intersection 8H sub I is a superset K sub j plus 1 of K sub j intersection H sub I plus 1 is a superset ... from the Zassenhaus lemma. H sub I plus 1 of H sub I intersection K sub j divides H sub I plus 1 of H sub I intersection K sub j plus 1 is equal to K sub j plus 1 of K sub j intersection H sub I divides K sub j plus 1 times K sub j intersection H sub I plus 1. Hence, we have the desired result. And again, this is Angel Tambak. Thank you.